Tonight, we're going to explore a question that sounds so simple a child could ask it, but so profound that it stumped some of the greatest minds in history for centuries. If the universe is filled with stars, hundreds of billions of them in our galaxy alone, and trillions of galaxies beyond that, then why? When you look up at the night sky, is it dark? Think about that. Stars in every direction. An almost incomprehensible number of them scattered across the cosmos. If they're everywhere, the sky should be blazing with light. Every single point you look at should eventually end at a star. The entire night sky should glow as bright as the surface of the sun. But it doesn't. The sky is dark. And the reason it's dark reveals something extraordinary about the universe we live in. Before we dive into this, if you find these kinds of deep explorations of the cosmos fascinating, a quick like or subscribe really helps the channel out. It's a small thing, but it means more than you know. Now, let's begin. I'll go outside tonight, find somewhere reasonably dark, away from the worst of the city lights, and look up. What do you see? Stars. Some bright, some faint, scattered across a black sky. If you're lucky enough to be somewhere truly remote, you might see the pale band of the Milky Way stretching overhead, a river of light made up of billions of stars too distant to distinguish individually. It's beautiful. It's humbling. And most people never think twice about it. The sky is dark with points of light in it. That's just how it is. That's how it's always been. It seems obvious, natural, unremarkable. But here's the thing. It shouldn't be that way. Not if the universe works the way people assumed it did for most of human history. For centuries, most thinkers assumed the universe was infinite. Not just big, but truly infinite. Stars stretching outward in every direction without end, and they assumed the universe was eternal. It had always existed and would always exist. It had no beginning and no end. The stars had been shining forever and would continue shining forever. These seemed like reasonable assumptions. The universe appeared static and unchanging. The same constellations that the ancient Greeks saw were the same constellations visible thousands of years later. Nothing seemed to be moving on the larger scales. Nothing seemed to be changing. The universe just was. But if you accept those two assumptions, that the universe is infinite in size and eternal in age, then something very strange follows. Something that directly contradicts what you see when you look up at night. If stars are scattered throughout an infinite universe, and they've been shining forever, then no matter which direction you look, your line of sight should eventually land on the surface of a star. Think about that carefully. Pick any direction at all. Look straight up. Look to the left. Look toward the horizon. In an infinite universe filled with stars, if you draw a straight line from your eye in any direction and extend that line far enough, it must eventually hit a star. It doesn't matter how far away that star is. It could be billions or trillions of miles away. It could be unimaginably distant. But in an infinite universe, there's always another star farther out. Your line of sight has to terminate at a stellar surface eventually because there are infinitely many stars in every direction. No line of sight can go on forever without encountering one. Now, if every line of sight ends at a star, then every point in the sky should be as bright as the surface of a star. Not as bright as a distant star appears to us, diminished by distance, but as bright as the actual surface of that star, because every direction is covered. Every tiny patch of sky, no matter how small, should have a star behind it somewhere. The entire sky, every single point of it, should be glowing with the light of stellar surfaces. The night sky shouldn't be dark, with points of light scattered through it. It should be a solid wall of light, uniform, blazing. Everywhere you look, in every direction, the sky should be roughly as bright as the surface of the sun. Not because the sun is special, but because the average star has a surface, and if you're looking at a surface in every direction, the sky should glow with the combined brightness of all those surfaces. The night should be as bright as day, actually brighter than day, because during the day you're seeing light from one star, our sun. At night, in this scenario, you'd be seeing the combined light from an infinite number of stars in every direction. The entire sky, from horizon to horizon, should be ablaze, but it isn't. The sky is dark, overwhelmingly, obviously dark. The darkness between the stars is vast and deep and unmistakable. You see a few thousand stars with the naked eye, scattered across a black canvas that covers most of the sky. The darkness isn't a subtle thing you need instruments to detect. It's the dominant feature of the night sky. It's what you see first when you look up. Darkness, punctuated by points of light. This is so obviously true, so plainly visible to anyone who has ever looked up at night, that it seems absurd to even question it. Of course the sky is dark. Everyone knows the sky is dark at night, but that's precisely the point. If the universe is infinite and eternal and filled with stars, the sky should not be dark. The fact that it is dark means something is wrong with those assumptions. Something fundamental about the universe is different from what people believed for centuries, and for a very long time, nobody could figure out what it was. This puzzle has a name. It's called Olbers Paradox, named after the German astronomer Heinrich Wilhelm Olbers, who described it in 1823. But Olbers wasn't the first person to notice the problem, not by a long shot. The contradiction had been lurking in the background of astronomy for centuries before Olbers put his name on it. The first person known to have clearly stated the problem was Johannes Kepler, the great German astronomer and mathematician back in 1610. Kepler was one of the most brilliant minds in the history of science. He's best known for discovering that planets orbit the sun in ellipses rather than perfect circles. His 3 laws of planetary motion laid the groundwork for Isaac Newton's theory of gravity. Kepler was a careful thinker, precise and mathematical, and he noticed something that others had overlooked. He argued that the darkness of the night sky was evidence that the universe could not be infinite. His reasoning was straightforward. If stars filled an infinite space, the sky would be completely covered in starlight. Since the sky is dark, the universe must have a boundary. The stars must end somewhere. There must be a dark wall beyond the most distant stars where no more light originates. For Kepler, the dark night sky was proof that the cosmos was finite. This was a radical idea at the time. Most European thinkers in the early 1600s were influenced by the ancient Greeks, many of whom believed in an infinite or at least extremely large cosmos. The idea that the universe had an edge, a boundary beyond which there was nothing, was unsettling. What would that boundary look like? What was beyond it? If there was nothing beyond the stars, what did nothing mean? These questions made people uncomfortable, and Kepler's argument didn't gain much traction. It was easier to assume the universe was infinite, and not worry too much about the brightness of the night sky. More than a century later, the problem resurfaced. In 1720, The English astronomer Edmund Halley, the same Halley who predicted the return of the famous comet that bears his name, addressed the issue. Halley argued that the problem wasn't as serious as Kepler had suggested. He proposed that very distant stars would simply be too faint to see. Their light would be so diminished by the vast distances involved that it wouldn't contribute meaningfully to the brightness of the sky. The distant stars would effectively be invisible, and the sky would remain dark. This sounds reasonable at first. After all, we know from everyday experience that distant lights appear dimmer than nearby ones. A street light a block away is bright. The same street light a mile away is much dimmer. A candle seen from across a city would be barely visible. So why shouldn't distant stars be too faint to matter? But Halley's reasoning contained a flaw, and it's a devastating one. Yes, individual stars get dimmer with distance. That's true. A star twice as far away appears 4 times dimmer. But Halley forgot to account for something. In an infinite universe, as you look farther out, there are also more stars. And not just a few more. The number of additional stars at each greater distance grows at exactly the same rate as their individual brightness decreases. The two effects cancel perfectly. It doesn't matter how far away the stars are. The total light contributed by distant stars doesn't diminish as they recede. Halley thought distance would rescue the dark sky by making far-off stars too faint to notice. But the mathematics of an infinite universe are ruthless. What you lose in brightness from each individual star, you gain back from the sheer number of stars at that distance. There's no net dimming, no savings. The infinite universe gives back with one hand exactly what it takes with the other. We'll examine this mathematics more closely when we look at why all the simple solutions to the paradox fail. For now, the key point is this. Halley's intuitive answer, that distant stars are just too dim to matter, doesn't survive mathematical scrutiny. Distance cannot save us. In an infinite universe, the contribution of distant stars never fades. It just keeps adding up, shell after shell, forever. And the total is catastrophic. A few decades after Halley, in 1744, a Swiss astronomer named Jean-Philippe Laux de Chezeaux laid out the mathematics of the problem in more rigorous detail. Chezeaux carefully calculated how the number of stars in each shell grows with distance, and how the brightness of each star diminishes with distance. He confirmed that the two effects balance perfectly, and that in an infinite universe, the sky should indeed be blindingly bright. Chezeaux then proposed his own solution. He suggested that some kind of material between the stars, perhaps a thin fluid or cosmic dust, was absorbing the light from distant stars. This interstellar medium would dim the light passing through it, so that stars beyond a certain distance would be effectively invisible. Their light would be absorbed before it reached us. This seemed like a reasonable hypothesis. We now know that interstellar space is indeed filled with gas and dust that can absorb light. When you look at photographs of our galaxy, you can see dark lanes and patches where dust clouds block the light from more distant stars. The dust is real. It's there. It does absorb light. But as we'll explore later, this solution has a fatal flaw. A flaw that wouldn't be fully understood for more than a century. Then came Olbers himself. Heinrich Wilhelm Olbers was a German physician and amateur astronomer. He practiced medicine during the day and observed the sky at night. He discovered several comets and asteroids, including the asteroid Pallas in 1802. In 1823, Olbers published a paper in which he clearly stated the paradox and proposed his own solution. Like Chazot before him, Olbers suggested that interstellar matter absorbed the light from distant stars. He argued that this absorbing medium was spread throughout space and that it blocked enough light to keep the sky dark. Olbers's name stuck to the paradox, even though he wasn't the first to describe it, partly because his paper was widely read and clearly written, and partly because science sometimes attaches names somewhat arbitrarily. The paradox became known as Olbers Paradox, and that's the name it carries to this day. But let's go back to the core of the problem, because it's crucial to understand just how inescapable this paradox is if you accept the assumptions behind it. The logic is surprisingly simple and surprisingly airtight. Assume the universe is infinite in extent. Stars go on forever in every direction. Assume the universe is eternal. It has existed forever, and will exist forever. The stars have been shining for an infinite amount of time. Assume the universe is static. It's not expanding or contracting. Space isn't stretching or shrinking. Everything is roughly where it's always been. Under these three assumptions, the paradox follows with mathematical certainty. You cannot escape it. The sky must be bright. Here's another way to think about it. Imagine you're standing in the middle of an infinite forest. Trees stretch in every direction as far as you can see and far beyond that. They go on forever. Now, look in any direction. Can you see through the forest to some open space beyond? No. No matter which direction you look, your line of sight is blocked by a tree trunk. Maybe the nearest tree is close. Maybe you can see past several trees before your view is blocked. But eventually a tree trunk crosses your line of sight. There's no direction you can look where you see anything other than tree trunks. Your entire visual field is filled with the surfaces of trees. This is exactly the same logic that applies to stars in an infinite universe. In an infinite forest, every line of sight hits a tree. In an infinite universe, every line of sight hits a star. The size of the trees doesn't matter. The spacing doesn't matter. As long as the forest is truly infinite, there's no way to see past all the trees. Every direction is blocked. And if instead of trees, we're talking about stars, then every direction shows you a glowing stellar surface. The sky is entirely covered. Now, you might think that the fact that stars are very small, compared to the distances between them, would solve the problem. And it's true that stars are tiny relative to the gaps between them. Our sun has a diameter of about 864,000 miles. The nearest star, Proxima Centauri, is about 4.24 light years away, which is roughly 25 trillion miles. That's an enormous ratio. The gap between stars is millions of times larger than the stars themselves. So, in any given direction, the chances of your line of sight hitting a nearby star are extremely small. But that's where infinity comes in. In an infinite universe, you're not just looking at the nearby stars. You're looking at all the stars, out to infinite distance. And while the probability of hitting a star in any small patch of sky is low for nearby stars, it increases as you include more and more distant stars. Each additional shell of stars adds more chances for your line of sight to be intercepted. Over an infinite distance, the probability doesn't just increase, it reaches 100%. Every line of sight is eventually blocked. It might take an incredibly long distance, but in an infinite universe, distance is not a constraint. There's always more distance available. Every line of sight, without exception, ends at a stellar surface. Let me make this even more concrete with some actual numbers. Astronomers have estimated that in a universe matching the assumptions of the paradox, the average line of sight would need to travel about 100,000 billion miles before hitting a star. That's a staggeringly large distance, far larger than what we'd now call the observable universe. But in a truly infinite universe, that distance is nothing. It's a finite number, and infinity dwarfs every finite number. In an infinite universe, every line of sight extends far enough to hit a star, no matter how far that might be. The conclusion is inescapable. Every point in the sky is covered. There's one more subtlety that makes the paradox even more stubborn. You might wonder about the effect of nearest stars blocking the light from more distant ones. In the forest analogy, the nearest trees block your view of the trees behind them. So, you don't actually see infinitely many trees. You only see the first tree in each direction. The same is true with stars. In an infinite universe, the nearest stars along any line of sight would block the light from the stars behind them. So, the sky wouldn't be infinitely bright. It would be bright, but limited to the average surface brightness of a star. This actually makes the prediction more specific. The entire sky should glow with a brightness roughly equal to the average surface temperature of a typical star. For a star like our Sun, the surface temperature is about 5,500 degrees Celsius, and it glows with a specific brightness. In an infinite, eternal static universe, every point in the sky would glow at roughly this brightness. The entire sky would look like the surface of a star. Not infinitely bright, but extraordinarily bright. Blindingly, impossibly bright. Bright enough to make life as we know it completely impossible. The Earth's surface would be heated to thousands of degrees. The oceans would boil. The atmosphere would be stripped away. No planet could maintain its structure in a universe where every direction poured stellar radiation onto it. And yet, the sky is dark. Comfortably dark. You can look up on a clear night and see deep, profound darkness stretching between the stars. The temperature of space between the stars is roughly 270 degrees below 0 Celsius, about 2.7 degrees above absolute zero. That's about as far from the surface temperature of a star as you can get. The observed sky isn't just a little dimmer than the paradox predicts. It's catastrophically dimmer by many orders of magnitude. Whatever is resolving this paradox isn't making a subtle adjustment. It's fundamentally changing the answer. This is what makes Olbers Paradox so remarkable. It's not a minor technical quibble about astronomical measurements. It's a fundamental question about the nature of the universe itself. The darkness of the night sky is telling us something profound about the cosmos. It's telling us that at least one of the assumptions behind the paradox must be wrong. Either the universe is not infinite, or it is not eternal, or it is not static, or some combination of these. The dark sky is not just an absence of light. It's a cosmic message, a clue written across the heavens that humanity stared at for thousands of years before understanding what it meant. And for centuries, the greatest minds in astronomy tried to figure it out. Kepler thought the universe must be finite. Halley thought distant stars were just too dim. Chasseau and Olbers thought interstellar dust was absorbing the light. Each of these ideas seemed plausible on the surface. Each of them seemed like it could solve the problem. But as we'll see, none of them actually work. The paradox is tougher than it looks. It resists easy answers. It demands something deeper, something more fundamental than a simple tweak to how we think about stars and light and distance. The real solution required a complete revolution in how we understand the universe. It required discoveries that wouldn't come until the 20th century. Discoveries about the nature of space and time themselves, about the origin of the cosmos, and about the fate of everything that exists. The darkness of the night sky isn't just a puzzle about stars. It's a doorway into the deepest questions cosmology has ever faced. And to walk through that doorway, we first need to understand why the simpler answers fail, why dust doesn't solve the problem, why distance doesn't help, why the only true resolution requires us to abandon the ancient assumption that the universe has existed forever and will continue unchanged for eternity. What's truly remarkable about all of this is that the answer was hiding in plain sight the entire time. Every single human who ever lived saw the evidence every clear night. Every person who ever looked up at a dark sky was seeing the answer to one of the most profound questions in all of physics. They just didn't know what they were looking at. The darkness wasn't nothing. It wasn't just the absence of light. It was information. It was the universe telling anyone who cared to listen that it had a beginning, that it was changing, that it was not what it appeared to be. For thousands of years, that message went unheard. People looked up, saw the dark sky, and assumed that's just how things were. They never stopped to ask why the sky was dark instead of bright. They never realized that the darkness itself was the most important observation anyone could make about the cosmos. It took centuries of careful thought, failed hypotheses, mathematical arguments, and eventually a revolution in physics to decode what the darkness was saying. And the answer, when it finally came, was more astonishing than anyone could have imagined. It revealed that the universe had a beginning, that space itself is expanding, that the cosmos is not eternal, not static, not unchanging. All of this encoded in something as simple and everyday as the darkness of the night sky. Now that you understand the paradox, now that you see why an infinite, eternal, static universe should produce a blazing sky instead of a dark one, the natural next step is to try to solve it. And over the centuries, many brilliant people tried. They came up with explanations that seemed perfectly reasonable on the surface. Ideas that felt like they should work. Ideas that, when you first hear them, sound so sensible that you might wonder why the paradox is considered a paradox at all. But every single one of these solutions fails. Not because they're poorly thought out, but because the paradox is deeper and more stubborn than it appears. Each proposed solution runs into a wall, some fundamental physical principle that blocks it from actually working. Understanding why these solutions fail is just as important as understanding the real solution, because it shows us exactly how trapped you are if you insist on believing in an infinite, eternal, static universe. The darkness of the sky cannot be explained within that framework. No clever trick saves you. No workaround rescues the old assumptions. The paradox demands something more radical. But let's walk through the failed solutions one by one, because each one teaches us something important. The most common answer people give when they first hear about Olbers' paradox is dust. There must be dust and gas between the stars, they say, and that material absorbs the starlight before it reaches us. This is the same solution that Chezeaux proposed in 1744 and that Olbers himself favoured in 1823. And on the surface, it seems completely reasonable. We know that interstellar space is not perfectly empty. It's filled with clouds of gas and dust, thin wisps of material left over from the formation of stars, or ejected by dying stars. When you look at photographs of our galaxy, you can clearly see dark patches and lanes where dust clouds block the light from more distant stars. The dust is real. It's there, it's measurable, and it does absorb visible light. Starlight passing through a dust cloud gets dimmed, sometimes dramatically. Some of the most beautiful nebulae in the sky are dark nebulae, regions where thick clouds of dust completely block the light from everything behind them. So why doesn't this solve the paradox? The answer lies in a fundamental principle of thermodynamics. Energy cannot be destroyed. It can only be transformed from one form to another. When dust absorbs light, it absorbs energy. That energy doesn't vanish. It has to go somewhere. What happens is that the dust heats up. The absorbed energy raises the temperature of the dust particles, and as the dust heats up, it begins to radiate energy of its own. This is a basic physical fact. Every object with a temperature above absolute zero emits radiation. The hotter the object, the more radiation it emits, and the shorter the wavelength of that radiation. A cool dust grain might emit infrared radiation, which your eyes can't see. But if the dust keeps absorbing more and more starlight, it keeps getting hotter and hotter. In an infinite, eternal universe where starlight has been streaming through space forever, the dust would absorb light for an infinite amount of time. It would keep heating up until it reached thermal equilibrium with the radiation surrounding it. And at thermal equilibrium, the dust would be re-emitting exactly as much energy as it absorbs. It would glow. It would glow at the same brightness as the radiation field surrounding it, which is the combined brightness of all those stars. Think about it this way. Imagine you have a room filled with heaters. The heaters are pumping out heat constantly. Now you put up a screen between yourself and the heaters. Initially, the screen blocks the heat. You feel cooler. But the screen is absorbing all that heat energy, and as it does, it warms up. Eventually, the screen itself becomes hot and starts radiating heat toward you. Given enough time, the screen reaches the same temperature as the heaters, and you feel exactly as warm as you would without the screen. The screen hasn't reduced the total heat in the room. It's just delayed it temporarily. Eventually, everything reaches the same temperature and the screen glows just as brightly as the heaters behind it. Dust in space works exactly the same way. In an eternal universe, dust clouds would absorb starlight, heat it up, and eventually reach thermal equilibrium with the starlight radiation. At that point, they'd be glowing just as brightly as the stars they're supposedly blocking. The dust wouldn't create dark patches in the sky. It would create bright patches, glowing patches that emit just as much light as the stars behind them. You'd look at the sky and see dust clouds glowing with the same intensity as stellar surfaces. The sky would still be uniformly bright. You'd just be seeing glowing dust instead of glowing stars, but the total brightness would be exactly the same. This is a rigorous thermodynamic argument, and there's no way around it. You cannot permanently hide energy by putting something in its path. All you can do is delay it. In a universe that's existed for a finite amount of time, dust can temporarily block light because it hasn't had time to reach thermal equilibrium. But in an eternal universe, infinite time means equilibrium is guaranteed. Every dust grain, every gas cloud, every object in the universe would eventually reach the temperature of the surrounding radiation field. Everything would glow. The darkness you're trying to create by invoking dust would be filled in by the dust's own radiation. The English astronomer John Herschel recognized this problem in the 1840s. He pointed out that any absorbing medium placed between stars and observer would eventually heat up and glow. The absorption solution is self-defeating. It solves nothing. It merely interposes a glowing screen between you and the stars, which is no different from seeing the stars directly. So dust doesn't work. What about the next obvious suggestion? Stars are really far away, and distant things appear dimmer. If the most distant stars are incredibly faint, maybe they just don't contribute enough light to matter. We touched on this earlier with Halley's argument, but it deserves a more detailed examination because it's such an intuitive idea. Yes, light from a distant source appears dimmer. This follows the inverse square law. If you double the distance to a light source, it appears 4 times dimmer. Triple the distance, 9 times dimmer. 10 times the distance, 100 times dimmer. This is because the light spreads out over an ever larger area as it travels. A star emits light in all directions, and by the time that light reaches you, it's been spread across a huge sphere. The farther you are from the star, the larger that sphere is, and the smaller the fraction of the total light that enters your eye or telescope. This is why the Sun, which is a fairly ordinary star, appears so bright compared to other stars. It's not that the Sun is special, it's that the Sun is close. If you move the Sun to the distance of Sirius, about 8.6 light years away, it would appear as just another star in the sky, not particularly remarkable. So distant stars are very dim. Stars that are billions of light years away would appear incredibly faint, vanishingly faint, so faint that you'd need the most powerful telescopes ever built just to detect them individually. Surely their contribution to the total brightness of the sky is negligible. The problem is that while each individual distant star is dim, there are enormously more distant stars than nearby ones. This is the shell argument, and it's mathematically airtight. Imagine dividing the universe into thin concentric shells, like the layers of an onion, centered on Earth. The innermost shell might extend from 0 to 1 light year away, the next shell from 1 to 2 light years, the next from 2 to 3, and so on, out to infinity. Each shell has a certain thickness and a certain radius. As the radius increases, the volume of each shell increases. Specifically, the volume increases with the square of the radius. A shell at twice the distance has 4 times the volume. A shell at 10 times the distance has 100 times the volume. And if stars are distributed roughly uniformly through space, then the number of stars in each shell also increases with the square of the distance. A shell at twice the distance contains 4 times as many stars. A shell at 10 times the distance contains 100 times as many stars. But the brightness of each individual star decreases with the square of the distance. A star at twice the distance appears 4 times dimmer. A star at 10 times the distance appears 100 times dimmer. Now, multiply these two effects together. In each shell, the number of stars goes up as the square of the distance, and the brightness of each star goes down as the square of the distance. These two factors cancel perfectly. The total brightness contributed by each shell is the same, regardless of how far away that shell is. The nearest shell and the most distant shell contribute the same total amount of light. If there were only a few shells, this would be fine. The total brightness would be modest and manageable, but in an infinite universe, there are infinitely many shells, and if each shell contributes the same finite amount of brightness, the total is infinite. The sum of infinitely many equal positive numbers is infinite. The sky should be infinitely bright. Now, as we discussed, the blocking effect of nearer stars prevents the brightness from actually being infinite. Stars in the foreground block stars in the background, just as trees in the foreground block trees in the background in a forest. This caps the total brightness at the average surface brightness of a star, rather than infinity. But that's still devastatingly bright. The entire sky at the temperature of a stellar surface would make life impossible. So the distance argument fails completely. It doesn't matter that individual distant stars are faint. The sheer number of them at great distances compensates exactly for their faintness. Distance does not dim the sky in an infinite universe. What about the next attempt? Maybe there just aren't enough stars. Maybe the universe has a lot of stars, but not enough to actually cover every direction. After all, stars are tiny compared to the spaces between them. Our sun occupies an infinitesimally small fraction of the sky, as seen from even the nearest star. Maybe even an infinite universe doesn't have enough stars to cover every single line of sight. This sounds plausible, but it misunderstands what infinity means in this context. If the universe is truly infinite in extent and stars are distributed with some average density throughout that infinite volume, then there are infinitely many stars. Not just a large number, not just a staggeringly large number, infinitely many. And infinitely many stars, even if each one covers only a tiny fraction of the sky, will collectively cover the entire sky. Here's why. Each star, no matter how distant, covers some tiny solid angle as seen from Earth. It might be an incredibly small angle, a minuscule fraction of a degree, but it's not zero. Any object with a finite size subtends a non-zero angle from any finite distance. In an infinite universe, you have infinitely many stars, each covering a small but non-zero angle. The total coverage is the sum of infinitely many small but non-zero contributions. This is like asking whether infinitely many small coins can cover the floor of a room. Each coin covers a small area. But if you have infinitely many of them, you can cover any floor, no matter how large. In fact, you can cover infinitely many floors. Infinity is powerful. It overwhelms any finite deficit. No matter how sparse the stars are, no matter how tiny each one appears, in a truly infinite universe with a uniform distribution of stars, every line of sight will eventually hit one. The coverage is complete. So no, the argument that there aren't enough stars doesn't work either, as long as we're talking about a genuinely infinite universe. There are always enough stars. Infinity guarantees it. Another attempt at it. Solution involves the idea that stars don't live forever. This is actually a more sophisticated argument than the previous ones, and it gets closer to the truth, though it still doesn't fully resolve the paradox under the original assumptions. Stars have finite lifetimes. Our sun has been burning for about 4.6 billion years, and will continue for another 5 billion years or so before it exhausts its hydrogen fuel and enters the final stages of its life. Massive stars burn through their fuel much faster. A star 10 times the mass of the sun might last only about 20 million years before exploding as a supernova. Even the longest-lived stars, small red dwarfs that burn their fuel very slowly, have theoretical lifetimes measured in trillions of years. But trillions of years is still not forever. So in a universe where stars have finite lifetimes, not every star that ever existed is still shining. Many stars have already died. Their light traveled through space for a while, but they stopped emitting new light when they died. This means the total amount of light filling the universe at any given moment is less than it would be if every star that ever existed were still shining. This seems helpful. Fewer active light sources means less total light, which should mean a dimmer sky. But here's the catch. In the eternal universe we're imagining, stars don't just die. New stars also form, Old stars die, but new stars are born from the gas and dust left behind. In fact, many new stars form from the remnants of old stars. Supernovae scatter heavy elements into space, and those elements become part of the next generation of stars. As long as there's gas available and the processes of star formation continue, the death of old stars is balanced by the birth of new ones. In a truly eternal, infinite universe, this cycle of stellar birth and death would have been going on forever. At any given moment, there would be an enormous population of active, shining stars. Some would be young, some middle-aged, some near death. But the total number of active stars would remain roughly constant over time, because the birth rate and death rate would be in equilibrium. The number of stars contributing light at any given moment would still be infinite, because the universe is infinite. And we're back to the same problem. Infinite stars, even with finite individual lifetimes, still cover every line of sight if they're distributed throughout infinite space. There's an additional subtlety here. Even after a star dies, the light it emitted during its lifetime continues to travel through space. A star that died 1 billion years ago still has photons traveling through the void that left its surface before it expired. In an eternal universe, there's been an infinite amount of time for stars to shine and for their photons to fill space. Even if individual stars live for only a few billion years, the accumulated photons from an infinite history of star formation and destruction would fill space with light just as thoroughly as if every star were immortal. The finite lifetime of individual stars doesn't solve the paradox in an eternal universe, because the supply of photons is replenished endlessly. Let's consider yet another attempted solution. Maybe the universe has a hierarchical structure that reduces the number of stars in distant regions. This idea was explored by several thinkers, including the Swedish astronomer Carl Charlier in the early 20th century. Charlier proposed a model in which stars are grouped into clusters, which are grouped into larger clusters, which are grouped into even larger clusters, and so on, with each level of the hierarchy being more spread out than the last. In such a structure, the average density of stars would decrease as you look at larger and larger scales. The further out you go, the more sparse the stars become. If the density drops off fast enough with distance, it's possible that the total amount of light reaching Earth from all directions would be finite, and the sky would be dark. This is actually a mathematically valid solution under certain specific conditions. If the density of stars decreases rapidly enough with distance, following a specific mathematical relationship, the total light can converge to a finite value instead of diverging to infinity. And there is some truth to the idea that the universe has structure. We know that stars are grouped into galaxies, galaxies into clusters, clusters into superclusters, and superclusters into filaments of the cosmic web. The universe is not perfectly uniform. It has structure at many scales, but here's the problem. Observations show that the universe, on the very largest scales, actually is roughly uniform. This is known as the cosmological principle. When you average over sufficiently large volumes, hundreds of millions of light years across, the universe looks pretty much the same everywhere. The density of galaxies doesn't keep decreasing as you look at larger scales. It levels off. The hierarchical structure that Charlier proposed doesn't match what we actually observe. The cosmic web has structure, but that structure has a characteristic scale. Beyond a few 100 million light years, the web looks essentially the same everywhere. It's a uniform froth of filaments and voids. So while Charlie's hierarchical model is clever, it doesn't match reality. The real universe is too uniform on large scales for this solution to work. And in a truly uniform, infinite universe, the paradox stands. There's another clever attempt that's worth addressing. Maybe we're in a special location. Maybe the universe isn't uniform. Maybe there just happen to be fewer stars in our particular region of space, creating a local dark bubble. If we're in a void, a region with fewer stars than average, maybe that's why our sky is dark. This doesn't hold up for several reasons. First, our observations show that the universe is remarkably uniform on large scales. We're not in a particularly sparse region. The density of galaxies around us is typical of the universe as a whole. Second, even if we were in a local void, the paradox applies to the sky as a whole, from every direction. In an infinite universe, the light from infinitely many stars beyond the void would still reach us. Being in a void would reduce the contribution from nearby stars, but the contribution from distant shells would be unaffected. And as we've seen, the distant shells contribute just as much total light as the nearby ones. A local void would make essentially no difference to the overall brightness of the sky. Some have suggested that maybe gravity itself could dim the light. Light climbing out of a strong gravitational field loses energy. This is called gravitational redshift, and it's a real, measured effect. Light leaving the surface of a massive star is slightly redshifted. Its wavelength stretched by the effort of escaping the star's gravity. If starlight loses energy as it travels through the gravitational fields scattered throughout the universe, maybe this could reduce the total brightness of the sky. But this effect is far too small to solve the paradox. Gravitational redshift from ordinary stars is tiny, shifting the wavelength by only a small fraction. And while light does interact with gravity as it travels through space, passing through the gravitational fields of galaxies and clusters, these interactions don't systematically drain energy from light over cosmic distances in a way that would significantly dim the sky. In an infinite, eternal, static universe, the cumulative gravitational effects would reach equilibrium, just like the dust heating argument. Gravity doesn't provide an escape from the paradox. You might also wonder whether the light from very distant stars could somehow be scattered or deflected, so it doesn't reach us in a straight line. Maybe the light gets bounced around, redirected, dispersed. And it's true that light can be scattered by particles in space. Small dust grains and free electrons can deflect photons, changing their direction. This is why the sky around the sun appears bright during the day. Sunlight is scattered by molecules in Earth's atmosphere, redirecting it toward your eyes from directions other than the sun itself. But scattering doesn't remove light from the universe, it just redirects it. A photon that's scattered away from one observer is scattered toward another. In an infinite universe, the total amount of light remains the same regardless of how much scattering occurs. Scattering redistributes light, but doesn't reduce its total energy. The sky might look slightly different, more diffuse, more uniform, but it would still be just as bright overall. Scattering doesn't help. What about the idea that the universe might be infinite in size but contain only a finite number of stars? If there's a maximum number of stars, even in an infinite space, maybe they don't cover every line of sight. This is logically possible but physically strange. In known physics, matter tends to fill available space. If the universe is truly infinite, and the laws of physics are the same everywhere, there's no obvious reason why star formation would be limited to a finite region. Stars form wherever conditions are right, wherever gas clouds collapse under gravity. In an infinite universe with uniform conditions, star formation should occur everywhere, producing an infinite number of stars. To have a finite number of stars in an infinite universe, you'd need some special mechanism that turns off star formation beyond a certain point. There's no known physical reason for such a mechanism to exist. So while this solution is logically possible, it's physically unmotivated and doesn't match what we observe. Let's consider one more attempted solution that's slightly more subtle. Maybe the universe is infinite and eternal, but it hasn't always contained stars. Maybe stars only started forming at some point in the past, and before that, the universe existed, but was empty and dark. In this scenario, the universe itself is eternal, but star formation began at a specific time. This is actually close to the truth in some ways. Stars did begin forming at a specific time, a few 100 million years after the Big Bang. But in the framework of an eternal universe, this doesn't quite solve the paradox either. If the universe is eternal but stars have only existed for a finite time, then the situation is very similar to having a finite age universe. Stars have been shining for a finite time, so only a finite amount of light has been emitted, and only a finite amount has had time to reach us. This would indeed produce a dark sky, but it raises an awkward question. If the universe is eternal, why did stars only start forming at a particular moment? What changed? What triggered star formation after an eternity of nothing? In an eternal, static universe, there's no natural mechanism to suddenly start forming stars after an infinite period of inactivity. Something must have changed. Some condition must have shifted. And if something changed, the universe isn't truly static. This line of reasoning actually points toward the real solution. Something did change. The universe had a beginning. Conditions evolved. The cosmos went from a state where stars couldn't form to a state where they could. But that's not the framework of an eternal, static universe. That's the framework of a universe with a history, a beginning, an evolution. And once you accept that, you've left the assumptions of the paradox behind. This is the fundamental lesson of all these failed solutions. Within the framework of an infinite, eternal, static universe, the paradox cannot be solved. Every attempt to explain the dark sky while maintaining those three assumptions runs into a fundamental physical principle that blocks it. Dust heats up and re-radiates. Distance is compensated by the greater number of distant stars. Finite stellar lifetimes are compensated by ongoing star formation and the accumulated photons from an infinite history. Hierarchical structure doesn't match observations. Local voids don't help. Gravity is too weak. Scattering just redistributes light without removing it. Nothing works. The only way out is to abandon at least one of the three assumptions. The universe must be either not infinite, not eternal, or not static, or perhaps all three. The darkness of the night sky isn't just telling us something about stars and light, it's telling us something about the fundamental nature of the universe. It's telling us that the cosmos cannot be what people assumed it was for centuries. Something is profoundly different about the real universe compared to the simple, elegant picture of an infinite, eternal, unchanging cosmos filled with stars. And this is what makes Olbers' Paradox so powerful. It's not just an interesting puzzle, it's a diagnostic tool. It takes a simple observation, the dark sky, and uses it to test fundamental assumptions about the universe. And those assumptions fail the test catastrophically. The dark sky doesn't just suggest that the assumptions might be slightly off, it proves that they're fundamentally wrong. An infinite, eternal, static universe is flatly inconsistent with what we observe every single night. Something had to give, and what gave way was our entire understanding of the cosmos. The resolution of Olbers' paradox required nothing less than a revolution in physics, a complete reimagining of the universe, its origin, its age, and its fate. The darkness between the stars was the first hint, the first clue, that the universe was stranger and more wonderful than anyone had imagined. The solutions that failed were not failures of intelligence, they were failures of imagination. The people who proposed them were working within a framework that seemed perfectly reasonable at the time. An infinite, eternal universe was the default assumption for centuries. It seemed natural. It seemed obvious. Questioning it felt radical, almost absurd. But the dark sky kept insisting that something was wrong with the picture. And eventually, in the 20th century, science caught up with what the sky had been saying all along. So if none of the simple answers work, if dust can't solve it, if distance can't solve it, if blocking can't solve it, then what does solve it? What is actually responsible for the darkness of the night sky? The answer is one of the most profound discoveries in the entire history of science. And it comes down to this. The assumptions behind the paradox are wrong. Not slightly wrong. Not off by a small margin. Fundamentally, deeply, completely wrong. The universe is not infinite in age. It has not existed forever. The stars have not been shining for all eternity. The universe had a beginning, and that single fact, more than anything else, is why the night sky is dark. The universe is approximately 13.8 billion years old. It began in an event we call the Big Bang, a moment of extraordinary density and temperature from which all of space, all of matter, all of energy, and time itself emerged. Before the Big Bang, there was no before, at least not in any way that our current physics can describe. The universe didn't explode into existing empty space. Space itself came into being with the Big Bang. Time itself began. Everything we see around us, every star, every galaxy, every atom in your body, every photon of light traveling through the void, all of it traces back to that single origin, approximately 13.8 billion years ago. This means the stars have not been shining forever. They couldn't have been. The universe hasn't existed forever. The first stars didn't form until roughly 100 to 200 million years after the Big Bang. Before that, the universe was a hot, dense soup of particles and radiation, far too energetic for atoms to form, let alone for those atoms to collapse into stars. It took time for the universe to cool enough for hydrogen gas to collect into clouds, for those clouds to collapse under their own gravity, for the cores to become hot and dense enough to ignite nuclear fusion. The first stars flickered to life in a universe that was already hundreds of millions of years old. And the stars we see today have been shining for various amounts of time, but none of them for more than about 13.6 billion years at most. That's a long time by human standards, but it's not forever. And in the context of this paradox, the difference between a finite age and an infinite age is everything. Here's why. Light travels at a finite speed. This is one of the most fundamental facts in all of physics. Light moves at approximately 300,000 kilometers per second. That's fast. Extraordinarily fast. Fast enough to circle the entire Earth about 7.5 times in a single second. But it's not infinitely fast. Light takes time to travel from one place to another. Light from the sun takes about 8 minutes and 20 seconds to reach Earth. Light from the nearest star beyond our sun, Proxima Centauri, takes about 4 years and 3 months to reach us. Light from the center of our galaxy takes about 26,000 years. Light from the Andromeda galaxy, the nearest large galaxy, takes about 2.5 million years. Now combine these two facts. The universe has a finite age, and light has a finite speed. What follows is enormous. If the universe is 13.8 billion years old, and light travels at a fixed speed, then there is a maximum distance from which light could possibly have reached us. Light that started its journey 13.8 billion years ago has traveled 13.8 billion light years. Any star farther away than that, well, its light simply hasn't had time to arrive. It's still on its way. It's out there, traveling through space, moving toward us at 300,000 kilometers per second. But it hasn't reached Earth yet. It might not reach Earth for billions of years. Or, as we'll see, it might never reach us at all. This means we can only see a finite portion of the universe. There is a boundary around us, a cosmic horizon, beyond which we cannot see anything. Not because there's a wall or a barrier, not because the stars end, not because space itself stops, but simply because light from beyond the distance hasn't had enough time to reach us since the universe began. We call this the observable universe, and it has a definite size. Now, you might expect the observable universe to be 13.8 billion light years in radius, matching the age of the universe, but it's actually much larger than that. The observable universe has a radius of about 46.5 billion light years, making it about 93 billion light years across. This seems contradictory. How can we see things 46 billion light years away in a universe that's only 13.8 billion years old? The answer is that the universe has been expanding the entire time the light has been traveling. A photon that left a distant galaxy 13 billion years ago has been traveling toward us for 13 billion years. But during that time, the space between us and that galaxy has been stretching. The galaxy has been carried farther and farther away by the expansion of space. By the time the photon arrives at Earth, the galaxy that emitted it is now much farther away than it was when the light left. So the observable universe is larger than you'd naively expect, because expansion has been stretching space during the entire journey of every photon that reaches us. But regardless of whether the observable universe is 13.8 billion light years in radius, or 46.5 billion. Light years in radius, the key point is the same. It's finite. We can only see a finite volume of space. That finite volume contains a finite number of stars. And a finite number of stars, no matter how large that number is, cannot cover every single line of sight in the sky. Think back to the forest analogy. If you're standing in an infinite forest, every direction is blocked by a tree. But if the forest is finite, if it only extends a certain distance before stopping, then some lines of sight might pass through the entire forest without hitting a single tree. You'd see gaps between the trunks. You'd see darkness beyond the trees. This is exactly what's happening with the night sky. The observable universe is our finite forest of stars. It contains an enormous number of stars, more than most people could begin to imagine, but it's still a finite number. However vast, it's not infinite. And that distinction is everything. And when you do the math, when you calculate how much of the sky is actually covered by the visible disks of all those stars, the answer is an incredibly tiny fraction. The vast majority of lines of sight don't hit a star. They pass through the entire observable universe without encountering a single stellar surface. Those lines of sight see darkness. This is the primary resolution of Olbers' paradox. The universe has a finite age, light travels at a finite speed, and therefore we can only see a finite number of stars. That finite number, while enormous, is not nearly enough to cover the entire sky. Most of the sky is not occupied by a star, and so most of the sky is dark. But the finite age of the universe is only part of the answer. The other part involves something equally revolutionary: the expansion of the universe itself. The universe is not static. It's not sitting still. Space itself is expanding, carrying galaxies along with it like raisins in freezing dough. This expansion was first observed by the American astronomer Edwin Hubble in 1929. Hubble measured the distances to a number of galaxies and found that almost all of them were moving away from us. And the farther away a galaxy was, the faster it was receding. This relationship between distance and recession speed is now called Hubble's law, and it was one of the most important discoveries in the history of astronomy. Hubble's discovery didn't mean that galaxies were flying through space like bullets. It meant that space itself was expanding. The galaxies weren't moving through a fixed background. The background itself was stretching, carrying the galaxies with it. Imagine dots drawn on the surface of a balloon. As you inflate the balloon, the dots move apart. Not because any dot is moving across the surface, but because the surface itself is expanding. Every dot sees every other dot moving away, and the farther apart two dots are, the faster they recede from each other. This is what's happening with the universe. Space is expanding. Galaxies are being carried apart. And the greater the distance between two galaxies, the faster the expansion carries them apart. This expansion has a profound effect on light. When light travels through expanding space, its wavelength gets stretched. The wave gets pulled apart as the space it's moving through expands. This stretching of light's wavelength is called redshift, because visible light shifted to longer wavelengths moves toward the red end of the spectrum. Light from distant galaxies is redshifted because it's been traveling through expanding space for millions or billions of years. The farther away a galaxy is, the more its light has been redshifted, because the light has been traveling through expanding space for a longer time. Now here's where it gets really interesting for our paradox. Redshift doesn't just make light appear slightly more red. If the redshift is strong enough, it can push light entirely out of the visible spectrum. Visible light, the kind your eyes can detect, occupies a narrow band of wavelengths. Below that band is ultraviolet light, which you can't see. Above that band is infrared light, which you also can't see. If a star's light is redshifted enough, the visible light it emitted gets stretched into infrared wavelengths. Your eyes can't detect infrared. So even though the light is still there, still traveling through space, still carrying energy, you can't see it. It's invisible to you. For very distant objects, the redshift is extreme. Light that was originally emitted as visible light has been stretched so much by the expansion of space that it's now in the microwave part of the spectrum, or even the radio part. These are wavelengths that are completely invisible to the human eye. The light is still there, but it has been shifted so far beyond what our eyes can detect that as far as our vision is concerned, it doesn't exist. This means that the expansion of the universe is actively dimming the sky in two ways. First, it's reducing the energy of each individual photon. When a photon's wavelength is stretched, its energy decreases. A red-shifted photon carries less energy than it did when it was first emitted. So even if you could see in all wavelengths, the total energy arriving from distant stars would be reduced by the expansion. Second, and more dramatically for what we see with our eyes, the expansion is pushing the light from the most distant and numerous sources entirely out of the visible range. The farthest reaches of the observable universe are filled with galaxies, but their light has been so thoroughly redshifted that none of it is visible. It's all infrared, or microwave, or radio. To our eyes, those galaxies might as well not exist. They contribute nothing to the brightness of the visible sky. And this brings us to something truly extraordinary. Because in one sense, the sky actually is glowing everywhere. Just not in a way you can see. In 1964, two physicists named Arno Penzias and Robert E. Wilson made one of the most important discoveries in the history of cosmology. They were working at Bell Telephone Laboratories in New Jersey, using a large horn-shaped antenna that had been built for satellite communications. They kept picking up a faint static, a low hum of microwave radiation that seemed to come from everywhere in the sky. They couldn't get rid of it. They checked their equipment. They cleaned pigeon droppings from the antenna, thinking the birds might be causing interference. They pointed the antenna in different directions. The signal was always there, always the same, coming from every part of the sky equally. What Penzias and Wilson had stumbled onto was the cosmic microwave background radiation, often abbreviated as CMB. This is the afterglow of the Big Bang itself. It's the oldest light in the universe, and it fills the entire sky uniformly. When the universe was very young, less than about 380,000 years old, it was so hot and dense that it was essentially a glowing fog. Photons couldn't travel far before being absorbed and re-emitted by the dense plasma that filled all of space. But as the universe expanded and cooled, there came a moment when the temperature dropped enough for electrons to combine with nuclei to form neutral atoms. This event, called recombination, made the universe transparent for the first time. Suddenly, photons could travel freely without being constantly scattered. The light that was released at that moment, the light from the hot, glowing plasma of the early universe, has been traveling through space ever since. When it was first released, this light was extremely hot, about 3,000 degrees Celsius, glowing a deep orange-red color similar to the surface of a cool star. But that was 13.8 billion years ago. In the time since, the universe has expanded enormously. And as the universe expanded, this ancient light was stretched. Its wavelength grew longer and longer. Today, after 13.8 billion years of expansion, that original orange glow has been redshifted all the way down to microwave wavelengths. Its temperature has dropped from 3,000 degrees to just 2.725 degrees above absolute zero. Absolute zero is the coldest possible temperature, minus 273.15 degrees Celsius. The cosmic microwave background is barely above that. It's the faintest possible whisper of what was once a blinding glow. And here's the remarkable thing. This radiation fills the entire sky. Every direction you look, the cosmic microwave background is there. It's isotropic, meaning it looks the same in every direction to an extraordinary degree of precision. The whole sky is glowing with this ancient light. If your eyes could see microwaves instead of visible light, the sky would not be dark at all. It would glow uniformly in every direction, a faint but complete shell of light surrounding you from all sides. A sense, the prediction behind Olbers Paradox is partially correct. The sky is covered in radiation from every direction, but that radiation is not visible light from stars. It's the red-shifted remnant of the Big Bang itself, stretched by 13.8 billion years of cosmic expansion into wavelengths far too long for human eyes to detect. So, the darkness of the night sky is really a story about two things working together. The finite age of the universe limits how many stars we can see, and the expansion of the universe redshifts the light from the most distant sources out of the visible range. Both of these effects contribute to the darkness, and both of them arise from the same underlying reality. The universe is not eternal and static. It had a beginning, and it has been expanding ever since. Let me put some numbers on this to give you a sense of how these effects compare. Astronomers who have carefully studied the paradox estimate that the finite age of the universe is the dominant factor. Even if the universe weren't expanding, even if space was static but the universe still had a finite age of 13.8 billion years, the sky would still be overwhelmingly dark. There simply haven't been enough stars shining for enough time to fill the sky with light. The finite number of stars within the observable volume, combined with the finite time they've been shining, is not enough to cover every line of sight. The expansion and redshift make the sky even darker by further reducing the contribution of the most distant sources, but the primary reason is the finite age. This is worth emphasizing because it corrects a common misconception. Many people who have heard about Olbers Paradox think the answer is simply that the universe is expanding and light gets redshifted. That's part of the answer, but it's not the main part. The main part is simpler and more fundamental. The universe has a finite age, and light has a finite speed, and therefore we can only see a finite number of stars. That finite number doesn't fill the sky. The expansion contributes an additional effect, but even without it, the sky would still be dark. The darkness is primarily about age, not about expansion. Think about what this means. For centuries, people looked up at the dark sky and assumed it was just the natural state of things. They didn't realize that the darkness was carrying information. The dark sky is not simply an absence. It's not nothing. It's a direct consequence of the fact that the universe has a specific age, a specific history, and a specific way of evolving over time. Every time you look at the dark gaps between the stars, you're seeing evidence that the universe had a beginning. You're seeing the finite age of the cosmos written across the sky in the language of darkness. If the universe were truly eternal and static, those dark gaps wouldn't exist. The entire sky would blaze with starlight. The fact that you can see darkness at all tells you something profound about the nature of reality. There's a beautiful irony here. For most of human history, people thought the universe was eternal and unchanging. The heavens were the realm of perfection and permanence. The stars were fixed and immutable. The cosmos just was, had always been, and would always be. And the dark night sky, the most obvious observable feature of the universe, was actually screaming the opposite message the entire time. The darkness was telling anyone who would listen that the universe was not eternal, that it had a beginning, that it was changing and evolving. But nobody heard the message because nobody thought to ask the question. It took centuries of puzzling over a seemingly trivial observation, why is the sky dark, to arrive at one of the most revolutionary discoveries in human history. The universe had a beginning. The cosmos is not eternal. Time itself started 13.8 billion years ago. The discovery of the cosmic microwave, background in 1964, was the final confirmation of this picture. Before Penzias and Wilson's discovery, the Big Bang theory was one of several competing models for the origin of the universe. The main competitor was the steady state theory, which proposed that the universe had no beginning and no end. According to the steady state model, the universe was expanding, but new matter was constantly being created to fill the gaps, keeping the overall density constant. The universe looked the same at all times. It was eternal, even though it was expanding. The steady state theory was elegant and appealing. It avoided the uncomfortable question of what happened before the Big Bang, because there was no Big Bang. But the cosmic microwave background was a death blow to the steady state model. The CMB is exactly what you'd expect if the universe was once extremely hot and dense, and has been cooling and expanding ever since. The steady state model had no way to produce this uniform background radiation. If the universe had always been roughly as it is now, there was no reason for this microwave glow to exist. But it does exist. It's there, filling the sky, measurable with the right instruments, exactly matching the predictions of the Big Bang model. The temperature, the uniformity, the slight variations in brightness from one direction to another, all of it matches what Big Bang cosmology predicts with extraordinary precision. The resolution of Olbers Paradox and the discovery of the cosmic microwave background are deeply connected. Both point to the same truth. The universe is not eternal and static. It had a beginning. It's been expanding and cooling ever since. The darkness between the stars and the faint microwave glow that fills the sky are two sides of the same coin. One tells you what's missing from the visible sky, starlight that would be there if the universe were eternal. The other tells you what's actually filling the sky instead, ancient light from the dawn of the cosmos, stretched beyond visibility by billions of years of expansion. There's one more aspect of the expansion that's worth understanding, because it affects the paradox in a subtle but important way. The expansion of the universe is not just happening, it's accelerating. In 1998, two independent teams of astronomers made a shocking discovery. They were studying distant supernovae, the explosions of dying stars, using them as distance markers to measure how the expansion of the universe was changing over time. Everyone expected to find that the expansion was slowing down, pulled back by the gravitational attraction of all the matter in the universe. But that's not what they found. The expansion wasn't slowing down, it was speeding up. Distant galaxies were receding faster than expected. Something was pushing the universe apart with increasing force. This mysterious force was given the name dark energy, and it remains one of the biggest mysteries in all of physics. We have almost no idea what it is. We know it exists because we can measure its effects. It accounts for about 68% of the total energy content of the universe, but its nature is completely unknown. What we do know is that dark energy is causing the expansion of the universe to accelerate, and this has consequences for the night sky. As the expansion accelerates, distant galaxies recede from us faster and faster. Their light is redshifted more and more. Eventually, for galaxies that are far enough away, the expansion of space between us and them outpaces the speed of light. This doesn't violate the cosmic speed limit because the galaxies aren't moving through space faster than light. Space itself is expanding, and there's no limit on how fast space can expand. But the result is the same. Light from those galaxies can never reach us. They're beyond our cosmic horizon, not just temporarily, but permanently. no matter how long we wait, their light will never arrive. Those galaxies are lost to us forever. And as the expansion continues to accelerate, more and more galaxies will cross this horizon. The observable universe will shrink, not in actual size, but in terms of what we can see. Galaxies that we can observe today will gradually be carried away by the accelerating expansion. Their light will be redshifted further and further until it fades from view entirely. Over billions of years, the night sky will grow darker still. Not because the stars are going out, though that will happen eventually too, but because the expansion of space is carrying the light sources away faster than their light can reach us. The dark sky that we see today, the darkness that Olbers puzzled over, is only going to deepen with time. In the very far future, beings in our galaxy might look out and see nothing at all beyond their own galaxy. Every other galaxy will have been carried beyond the observable horizon by the accelerating expansion. The universe will appear to contain just one galaxy floating in an infinite void. The cosmic microwave background itself will be redshifted to ever longer wavelengths, growing colder and fainter until it becomes undetectable. The evidence that the universe once contained trillions of galaxies, that it began in a hot, dense state, that it has been expanding and cooling for billions of years, all of that evidence will be erased. Future astronomers, if they exist, will look out at a sky that contains only their own galaxy and nothing else. They might conclude, reasonably but wrongly, that their galaxy is all that exists. This is a sobering thought. We live in a special time in the history of the universe, a time when we can still see the evidence of the Big Bang, when we can still observe distant galaxies, when the cosmic microwave background is still detectable. A few 100 billion years from now, none of this will be visible. The clues that allowed us to unravel the history of the universe will have been swept away by the very expansion that created the darkness in the first place. We are fortunate to exist now, in this window of cosmic time when the universe still shows its hand. The darkness of the night sky, then, is not a simple thing. It's not just an absence of light. It's a direct, observable consequence of the most fundamental properties of the universe we inhabit. It tells us the universe has a finite age. It tells us light travels at a finite speed. It tells us space is expanding. It tells us the most distant light has been redshifted beyond our ability to see. It even hints at dark energy and the accelerating expansion that will shape the far future of the cosmos. All of this information is encoded in the simple darkness between the stars. You don't need a telescope to see it. You don't need any equipment at all. You just need to look up on a clear night and notice that the sky is dark. That darkness is data. That darkness is a message from the universe about its own nature, its own history, and its own fate. Penzias and Wilson received the Nobel Prize in Physics in 1978 for their discovery of the cosmic microwave background, and deservedly so. Their accidental discovery confirmed the Big Bang model, settled a decades-long debate about the origin of the universe, and provided the final piece of the puzzle that resolved a paradox that had baffled astronomers for centuries. The dark night sky, which had seemed like the most obvious and unremarkable thing in the world, turned out to be one of the most important observations in the history of science. It was a clue that the universe had a beginning. And once we understood that, everything changed. Our understanding of the cosmos, our understanding of time itself, Our understanding of where we came from and where we're going, all of it was transformed by the simple realization that the sky is dark because the universe is young. Not young by human standards, obviously. 13.8 billion years is an almost incomprehensible span of time. If you started counting seconds at the moment of the Big Bang and counted continuously without stopping, you'd reach a number with 17 digits. That's a long time, but it's not infinity. And in the context of this paradox, the distinction between a very long time and forever is everything. A universe that has existed for 13.8 billion years is a fundamentally different place than a universe that has existed forever. In a 13.8 billion year old universe, light has traveled a finite distance. We can only see a finite number of stars. The sky is dark. In an eternal universe, light from infinitely many stars would have had time to reach us. The sky would be bright. The fact that the sky is dark tells us with absolute certainty that we do not live in an eternal, static universe. We live in a universe with a history. A universe that began and has been evolving ever since. A universe whose story is still being written with every passing moment. So let's step back and truly appreciate what just happened. A child's question, maybe the simplest question anyone could ask about the night sky, why is it dark, led humanity to discover that the universe had a beginning. That space itself is expanding. That the cosmos is not eternal, not static, not unchanging. The darkness between the stars is not emptiness. It's not nothing. It's one of the most information-rich observations in all of science. Every time you look up at a dark sky, you are seeing direct physical evidence for the Big Bang, for cosmic expansion, for the finite age of the universe, and for the speed of light as a fundamental cosmic constant. All of that, encoded in simple darkness, in the absence of light, in the black gaps between the stars that most people never think twice about. Let's talk about what the observable universe actually means, because this concept is central to understanding why the sky looks the way it does. The observable universe is not the whole universe. It's the portion of the universe from which light has had time to reach us since the Big Bang. It's defined by a boundary called the cosmic horizon, and that boundary exists purely because of two facts. The universe has a finite age, and light has a finite speed. Nothing more complicated than that. 13.8 billion years of time multiplied by the speed of light gives you a distance. And that distance, modified by the expansion of space during the light's journey, defines a sphere around us roughly 93 billion light years in diameter. Everything inside that sphere is, in principle, observable. Everything outside it is not. Not because it doesn't exist, but because the light from those regions hasn't arrived yet, and due to the accelerating expansion, some of it never will. Within this observable sphere, astronomers have counted and estimated the contents with remarkable precision. There are approximately 2 trillion galaxies. Each galaxy contains anywhere from a few million to several trillion stars. The total number of stars in the observable universe is estimated at around 200 billion trillion. That's 2 followed by 23 zeros. It's a number so large that it defies any meaningful comparison to everyday experience. There are more stars in the observable universe than grains of sand on every beach on Earth. More stars than seconds that have elapsed since the Big Bang. More stars than words that every human who has ever lived has ever spoken. And yet, this absurdly enormous number of stars is not enough to fill the sky with light. That's how vast the observable universe is. 200 billion trillion stars scattered across 93 billion light years, and they still only cover an infinitesimally small fraction of the sky. The darkness between them is overwhelming. The darkness wins by an almost incomprehensible margin. Why? Because even though 200 billion trillion sounds like a lot, and it is a lot, it's still finite. And a finite number of stars spread across a finite volume of space simply cannot cover every direction. The total angular area of the sky that's actually covered by the visible disks of stars is a vanishingly small fraction of the total sky. If you added up the apparent sizes of every star in the observable universe, every single one, the combined area would cover far less than 1 trillionth of the total sky. The rest is empty, dark, devoid of starlight. And that's why the sky is dark. Not because stars are rare, but because space is vast beyond comprehension. The stars are numerous, but the voids between them are enormously more numerous still. This tells us something important about the geometry and structure of the universe. The cosmos is not a crowded room packed wall to wall with light sources. It's more like an ocean of darkness with tiny, widely scattered islands of light. Stars and galaxies are the exceptions, not the rule. Most of the universe, by volume, is empty space. Cold, dark, silent, and extending in every direction for distances that make the spaces between stars look cozy by comparison. The voids between galaxy clusters can span hundreds of millions of light years. Regions of space where almost nothing exists. No stars, no planets, no dust, no gas, just vacuum, stretching in every direction for distances that would take light itself hundreds of millions of years to cross. And within this vast, mostly empty cosmos, the finite age of the universe creates a hard limit on how much of it we can access. The observable universe is large, but it's bounded. It has a definite edge, not a physical wall, but an information horizon beyond which no signal has had time to reach us. The actual universe almost certainly extends far beyond this horizon. How far? We don't know. It might be a few times larger than what we can see. It might be thousands of times larger. It might be infinite. Current observations are consistent with a universe that could be infinite in extent. The geometry of space appears to be flat, or very nearly flat, and a flat universe can extend forever. If the universe is infinite, then the observable universe, with its 93 billion light-year diameter, and its 2 trillion galaxies, and its 200 billion trillion stars, is just a tiny patch. A single bubble of visibility in an ocean of space that stretches without limit in every direction. This puts the darkness of the sky into even sharper perspective. If the universe is infinite, there really are infinitely many stars out there. Olbers was right about that part. Stars in every direction, stretching outward forever, covering every possible line of sight if you go far enough. But most of those stars are beyond our cosmic horizon. Their light hasn't reached us. It's still on its way. Or because of the accelerating expansion, it will never arrive. The infinite starlight that would make the sky bright exists in principle, but is locked away behind the horizon. We can't see it. We'll never see it. The finite age of the universe acts as a filter, allowing in only a finite amount of light from a finite number of sources. And that finite amount is nowhere near enough to fill the sky. Now let's think about how the expansion of the universe shapes what we see. Because the expansion doesn't just limit the number of stars we can observe. It actively transforms the light that does reach us. Every photon traveling through expanding space gets stretched. its wavelength grows longer, its energy decreases, and over cosmic distances, this stretching becomes extreme. Light from a galaxy a few billion light years away might be redshifted by a factor of 2 or 3, meaning its wavelength has doubled or tripled since it was emitted. Light from the earliest galaxies, more than 13 billion light years away, can be redshifted by a factor of 10 or more. Ultraviolet light from those ancient galaxies has been stretched into infrared wavelengths by the time it reaches us. Visible light has been stretched into wavelengths far beyond what any human eye could detect. The most extreme example of this stretching is the cosmic microwave background we discussed earlier, the ancient afterglow of the Big Bang that fills the entire sky. To appreciate just how dramatically expansion has transformed this light, consider the numbers. Since that radiation was released, the universe has expanded by a factor of roughly 1,100. Every wavelength has been stretched by that same factor. Light that once had a wavelength of about 700 nanometers at the red end of the visible spectrum now has a wavelength of about 700,000 nanometers deep in the microwave range. If you could have been present at the moment of recombination, floating in the young universe just 380,000 years after the Big Bang, you would have seen the entire sky glowing a uniform deep orange in every direction. No darkness anywhere, no gaps, no stars, because stars hadn't formed yet. Just an all-encompassing glow of hot plasma filling every direction. Today, that same glow is still there. It still fills every direction. But it has been stretched so thoroughly by 13.8 billion years of expansion that it is completely invisible to human eyes. The universe did fill the sky with light, exactly as the paradox predicted. It just stretched that light into a form we cannot see. Since that initial detection, our ability to study this ancient radiation has improved dramatically. The COBE satellite in the early 1990s provided the first detailed measurements from space, confirming that the CMB has a perfect thermal spectrum, exactly what you'd expect from a universe that was once in thermal equilibrium. The WMAP satellite in the 2000s produced far more detailed maps, measuring temperature differences across the sky with a precision that was previously impossible. And the Planck satellite in the 2010s refined those measurements even further, producing the most detailed portrait of the early universe ever made. Each generation of instruments confirmed and sharpened the same picture. The CMB matches the predictions of Big Bang cosmology to a degree of accuracy that's almost unprecedented in science. The temperature is exactly what the models predict. The uniformity is exactly right. And the tiny deviations from perfect uniformity, the slight fluctuations in temperature from one patch of sky to another, match the theoretical predictions with extraordinary precision. And those tiny fluctuations in the CMB, the slight variations in temperature from one patch of sky to another, are themselves incredibly important. They represent the seeds of all the structure we see in the universe today. Those fluctuations correspond to regions in the early universe that were very slightly denser or very slightly less dense than average. Over billions of years, gravity amplified those differences. The denser regions attracted more matter, becoming galaxies and galaxy clusters. The less dense regions became the vast cosmic voids. The entire cosmic web, the filaments and walls and voids that span hundreds of millions of light years, all of it grew from those tiny temperature differences in the cosmic microwave background. The pattern of fluctuations in the CMB is essentially a baby picture of the universe, showing the embryonic structures that would grow into everything we see around us today. Now, what does all of this mean for us and for our understanding of where we sit in cosmic history? Because the resolution of this paradox doesn't just tell us about the universe, it tells us something about the nature of scientific discovery itself. For centuries, the dark sky was simply accepted. It was background. It was the default state of the night. Nobody questioned it because it seemed too obvious to question. And that's precisely what made the paradox so powerful when it was finally recognized. The most obvious things are often the hardest to see clearly. It took extraordinary minds to look at something everyone took for granted and ask why. Think about how many other obvious facts about the universe might be hiding profound truths. We see the sun rise every morning. For thousands of years, people assumed the sun moved around Earth. The obvious observation, sunrise, contained within it a deep truth about the structure of the solar system that took millennia to decode. We feel the ground beneath our feet as solid and still, but the ground is moving. The Earth is rotating at over 1,000 miles per hour at the equator and orbiting the sun at roughly 67,000 miles per hour. The ground isn't still, it just feels still because we're moving with it. Obvious observations, profound hidden truths. The dark night sky is perhaps the greatest example of this pattern. The most everyday observation in all of human experience, looking up and seeing darkness, turned out to contain the answer to one of the deepest questions in cosmology. There's also something worth noting about how this particular truth was uncovered. It wasn't a single brilliant discovery by a single brilliant person. It was a slow accumulation of insights over centuries. Kepler noticed the problem in 1610, but drew the wrong conclusion, thinking the universe must simply have an edge. Halley tried to solve it in 1720, but got the physics wrong, thinking distance would dim the stars enough to save the old model. Chasseau and Olbers proposed dust, which sounded reasonable but fails on thermodynamic grounds. Each attempt failed, but each failure taught us something. Each wrong answer eliminated a possibility and narrowed the range of what the correct answer could be. Science doesn't always work through sudden flashes of genius. Sometimes it works through the slow, patient elimination of wrong ideas until only the truth remains. Olbers' Paradox is a masterclass in this process, and the truth that finally emerged was far stranger than any of the proposed solutions. Nobody imagined that the answer would be that the universe had a beginning. Nobody expected that space itself would turn out to be expanding, stretching light beyond visibility. These ideas were so radical, so far outside the framework that any of the earlier thinkers were working within, that they couldn't have been guessed. They had to be discovered through observation and mathematics, and the willingness to follow the evidence wherever it led, even when it led somewhere deeply uncomfortable. The accelerating expansion we discussed earlier means the darkness will only deepen over cosmic time. As we explored, the evidence we now rely on, the distant galaxies, the cosmic microwave background, the patterns that reveal the universe's history, all of it, will eventually be carried beyond detection by the same expansion that helped resolve the paradox in the first place. In roughly 100 billion years, future astronomers in our merged galaxy will look out and see nothing beyond their own shores. The Milky Way and Andromeda will have long since combined into a single large elliptical galaxy, and every other galaxy will have been pushed permanently beyond the observable horizon. The cosmic microwave background will have been stretched to wavelengths so long and temperatures so low that no instrument could ever detect it. The night sky of the far future will be darker than ours, and it will carry fewer clues about the universe's true nature. We are privileged observers. We exist in a narrow window of cosmic time when the universe still wears its history on its sleeve. The evidence is still readable, the story is still visible, and we were clever enough to decode it. That combination of cosmic timing and human curiosity is extraordinary. It might never happen again in quite the same way. There is something deeply poetic about the fact that the darkness of the night sky, the most common and seemingly mundane observation anyone can make, turns out to encode some of the deepest truths in all of science. You don't need a telescope to see it. You don't need any equipment at all. You don't need years of training or advanced mathematics. You just need to go outside on a clear night, look up, and notice that the sky between the stars is dark. That's it. That single observation, available to every human who has ever lived, contains within it the proof that the universe had a beginning, that space is expanding, that light has a finite speed, and that the cosmos is evolving over time. For thousands of years, nobody realized this. Billions of people looked up at the dark sky and never thought to ask why it was dark. They accepted it as a given, a basic fact of existence. Like the wetness of water or the hardness of stone. It never occurred to them that the darkness needed an explanation, let alone that the explanation would overturn everything humanity believed about the cosmos. The greatest cosmological clue in history was hiding in plain sight, visible to everyone, understood by no one, for millennia. And even now, most people who look up at the night sky don't realize what they're seeing. They see stars. They might notice planets or the moon. They might admire the beauty of it all. But they rarely think about the darkness itself. The darkness is background. It's what's left over after you notice the bright things. It's the canvas, not the painting. But in reality, the darkness is the most important thing in the sky. The darkness is the message. The darkness is the discovery. The stars are interesting, beautiful, and worthy of study. But the darkness between them is where the deepest truth lives. Let me tie this back to the paradox one final time. Olbers' paradox asks why the sky is dark. The answer involves three connected facts. 1, the universe has a finite age. 2, light travels at a finite speed. 3, the universe is expanding, redshifting distant light out of visibility. The finite age means we can only see a finite number of stars. The finite speed of light means there's a horizon beyond which we can't see. The expansion means that even the light that does reach us from the most distant sources has been stretched to wavelengths our eyes can't detect. Together, these three facts produce the dark sky we observe. They replace the assumptions of an infinite, eternal, static universe with the reality of a finite age, expanding, evolving cosmos. And the darkness, the simple, visible darkness between the stars, is the direct, inescapable consequence of that reality. Every other feature of the night sky can be understood through narrower, more specialized knowledge. Understanding why stars twinkle requires knowing about atmospheric turbulence. Understanding why planets don't twinkle requires knowing about angular size. Understanding the phases of the moon requires knowing about orbital geometry. But understanding why the sky is dark requires knowing about the origin and fate of the entire universe. It's the most fundamental observation you can make about the cosmos, and it demands the most fundamental answer. There's one more thing worth reflecting on. The darkness of the night sky is not just a clue about the past. It's also a statement about the future. The sky is dark because the universe is finite in age and expanding. And because the expansion is accelerating, the sky will continue to darken over cosmic time. Far in the future, as more galaxies are pushed beyond the horizon, as the cosmic microwave background fades to undetectability, as the stars in our own galaxy burn through their fuel and die, the sky will grow darker and darker. Billions of years from now, the last stars will exhaust their nuclear fuel. Red dwarfs, the most long-lived stars, will burn for trillions of years, but even they will eventually run out of hydrogen. When the last red dwarf flickers out, the universe will enter an era of darkness that will last far longer than the era of starlight. The age of stars. From the first stellar ignition a few 100 million years after the Big Bang to the death of the last red dwarf trillions of years in the future, will be a brief, bright chapter in a much longer story of darkness. After the stars die, the universe will contain only stellar remnants, white dwarfs cooling slowly toward absolute zero, neutron stars spinning down and dimming, black holes slowly evaporating through Hawking radiation over timescales so long they make the current age of the universe look like the blink of an eye. The largest supermassive black holes in the universe would take roughly 10 to the power of 100 years to evaporate. That's a 1 followed by 100 zeros. The current age of the universe, 13.8 billion years, is 10 to the power of 10. These timescales are so incomprehensibly vast that no analogy does them justice. The era of starlight, the era we live in, will be an unimaginably tiny fraction of the universe's total history. We exist during a brief flash of brightness in an overwhelmingly dark cosmos. And that brings us full circle. The night sky is dark. It seems obvious. It seems unremarkable. But it's one of the most important observations in the history of science. The darkness tells us the universe had a beginning. It tells us space is expanding. It tells us light has a finite speed and the cosmos has a finite age. It tells us the sky is not what it would be in an infinite, eternal, unchanging universe. Every gap between the stars is a window into the deepest truths of cosmology. Every patch of darkness is evidence for the Big Bang. Every black space between the constellations is a testament to the fact that the universe was born, is evolving, and will one day grow darker still. The next time you go outside on a clear night, look up. See the stars, yes. Admire them. Wonder about the worlds that might orbit them. But then look at the darkness between the stars. Really look at it. Let your eyes rest on that deep, quiet blackness. And remember what it means. That darkness is not empty. It's not nothing. It's the fingerprint of the Big Bang. It's the signature of cosmic expansion. It's proof that the universe has a finite age and a finite horizon. It's a message that has been written across the sky for 13.8 billion years, visible to every human who has ever looked up, understood by none of them until the 20th century, and now understood by you. You are standing on a small planet orbiting an ordinary star in a spiral galaxy that is one of roughly 2 trillion galaxies in the observable universe. That observable universe is a finite bubble of visibility in a cosmos that might extend forever. The stars you see are a tiny, local sample of a much larger population, most of which is beyond your horizon, invisible, unreachable. The light that fills the sky between the stars, the cosmic microwave background, is the cooled remnant of the universe's fiery birth, stretched to invisibility by 13.8 billion years of expansion. And the darkness, the deep, quiet, all-encompassing darkness that fills most of your view when you look up at night, is the most profound thing you will ever see. It is the universe telling you its own story. A story of origin, of expansion, of finite time and infinite space. A story that begins with a blinding flash and ends, trillions upon trillions of years from now, in silence and cold and the deepest darkness imaginable. But tonight, right now, the stars are still shining. The universe is still young enough for light and warmth and life. The darkness between the stars is still framed by starlight, still punctuated by points of brilliance, still beautiful in its contrast between light and void. We live in the bright chapter, the brief, fleeting, extraordinary chapter when the cosmos is illuminated and a species on a small world has learned to read the darkness and understand what it says. That's what the dark sky means. Not just the absence of light, but the presence of truth. A truth so fundamental that was written across the heavens from the very beginning, waiting patiently for someone to look up and finally understand. Thank you for joining me on this journey tonight. If you found this exploration meaningful, a like or subscribe would mean the world to me. It helps me keep making these deep dives into the cosmos and the questions that shape how we understand it. And the next time someone asks you why the sky is dark at night, you'll know the answer. It's not because space is empty. It's not because stars are far away. It's because the universe had a beginning. Because light takes time to travel. Because space itself is expanding, stretching, ancient light beyond what our eyes can see. The darkness is not an absence, it's a revelation. Sleep well tonight under a sky that's been trying to tell you its story for as long as the stars have been shining, and now you've heard it. Good night.